Hello and welcome to today's central exercise class. As usual, we'll be taking your questions on our chat. You can find the chat on chat.tum.de. Just log in with your TUM Online credentials if you haven't done so yet. And please ask your questions on this chat channel here, MA9714-CE. As usual, the chat will be moderated by Eileen Carlson. So we'll be discussing sheet number 5 today. Here's sheet number 5. And as you can see, the main topic of that sheet is differentiation in higher dimensions. And also we'll discuss polar coordinates a little. So we'll start right away with C5.1, where we have to determine the Jacobian matrix of functions that are multivariate. So we have multiple input variables here. But also that have a vector valued output. So up to this point, we have only considered functions with a real value as an output. And now we are also considering functions with vectors in the output. So in this case, R3. So you can see this function here that maps two input variables, x1 and x2, to a vector in R3. So that has three components here. And of course, we can generalize our definition of differentiation to that case here as well. And that leads to the notion of a Jacobi matrix or Jacobian of a function. So we'll determine the Jacobian of the two functions here in C5.1 first. Okay, let's see. The first function, let me write that down again, is f R2 to R3. And f of x1, x2 is defined as x1, x2 squared, x1 squared, x2, and x1 squared plus x2 squared. So three different components. The Jacobian is basically the collection of partial derivatives of that function. You're familiar with the gradient. That is the collection of partial derivatives of a real valued function. And the Jacobian basically does the same thing, but separately for each of these components here. So basically we compute the gradient of this function, then the gradient of this function, and then the gradient of this function. The difference is the gradient in this case always goes in the corresponding line. So the gradient for this function here will go into the first row of the Jacobian. So it'll be a row vector instead of a column vector that we'd usually use for the gradient. And basically that's the difference between the Jacobian and the gradient, if you want. So the Jacobian of that function here, let's start with, well, that's A, by the way, part A. Let's start with that. That's usually denoted by J for Jacobian, and then the function f as an index at the point x1, x2. That's simply obtained by taking the partial derivatives of these coordinate functions. So we'll usually denote the first function here, the first coordinate of that vector by f1. Then we'll denote the second coordinate by f2, sorry. And these functions, f1, f2, f3, these are all functions that map from R2 to R. So we can take the partial derivatives as usual. Let me just write the vector of partial derivatives in the corresponding rows. So this matrix will consist of the partial derivatives of f1 with respect to x1, then the partial derivative of f1 with respect to x2. That's row 1. In the second row, we'll do the same thing for f2. So we'll have df2, dx1, and dx2. And in the third row, the same for x3. So that's how you get the Jacobian. So as you can see, this is going to be a 3x2 matrix. We have 3 rows corresponding to this R3 here, the output. And we have 2 columns that correspond to the input, the dimension of the domain, basically. Okay, so what do we get here in this example? Now, if we differentiate this function here with respect to x1, we simply get x2 squared. If we differentiate that function with respect to x2, we get 2x1, x2. Similar for this function here, differentiating with respect to x1 yields 2x1, x2. And if we differentiate with respect to x2, then we get x1 squared. And now for the last row here, so x1 squared plus x2 squared, differentiating with respect to x1 yields 2x1. Differentiating with respect to x2 simply yields 2x2. So that is the Jacobian of that function f. Before we continue, any questions so far?
No, only about the holiday next week, but probably that makes more sense to do after.
Yeah, well, yeah, we probably should address that one. Remind me at the end if I forget.
Yeah.
Okay, then let's go right to the next one. That's part B. So in this case, we have a function that maps from R3 to R3, which means the Jacobian is going to be a 3x3 matrix now. Yeah, 3 input variables determine the columns, 3 output components determine the rows. And the function is defined as f of x1, x2, x3 is equal to e to the power of x1, e to the power of x1 plus x2, and then e to the power of x1 plus x2 plus x3. And again, computing the Jacobian simply means we compute the derivatives of each row, the partial derivatives of each row. So we start with this row here, e to the x1. Differentiating that with respect to x1 simply yields the same term again, e to the x1. Differentiating with respect to x2 yields 0 because there's no x2 in this expression. And the same is true for the partial derivative with respect to x3. Similarly for the second row here, differentiating with respect to x1 yields e to the power of x1 plus x2. Same is true for differentiating with respect to x2. And there's no x3 in that term, so the derivative with respect to x3 is again 0. And for the third row, so now we have all 3 variables in there, and the result is always the same, regardless of which variable we use. It's always e to the x1 plus x2 plus x3. So that is the Jacobian here. Okay, questions about B?
So far, I only see someone typing, so no.
Then let's continue first with C2.
Yeah.
This one is also on differentiation. So have a quick look at that. This time we have 2 functions. One function g that maps from R2 to R3, one f that maps from R3 to R. And what we are going to do, we're going to consider this function here, obtained by first applying g and then applying f to the result. And the question is, how can we determine the derivative of that function using the individual derivatives that we might already have? That's what this C52 does here. So let's first write down the functions again. So we have f. It's the outer function that maps R3 to R. And f is defined as f of x1, x2, x3 equals x1 squared e to the x2, x3. And we have g. It's going to be the inner function. G maps R2 to R3. And g of x1, x2 is defined as 2x1 plus x2, x1 minus x2, and x1. And our first task is to determine the derivatives of f and of g, respectively. So what we want is the derivatives, the differentials of f and of g. And basically, that means we're asking for the Jacobian or the gradient. So remember, the differential of a function is closely related to its gradient if that is a function that maps to R, and f does just that. And then its differential is the same as the gradient of f transposed. Or in other words, you could also say that is the Jacobian of f. So basically the difference between gradient and Jacobian for a real valued function is the gradient is usually a column vector and the Jacobian is usually a row vector. That mainly has historical reasons, and you might call that a little unfortunate, but that's just the way things are. Okay, so basically we're going to deal with the Jacobian, because for applying the rules of differentiation, the Jacobian is usually the best choice because it's the more general choice. It works in higher dimensions too, and you don't have to pay attention to whether you're working on columns or rows. The Jacobian will do the right thing. Okay, so only thing basically you need to know is for a real valued function, you have one component of that output vector. So the Jacobian is going to be a row vector. So let's compute that one. So JF of x1, x2, x3. So here's f again. Differentiating with respect to x1 first, that will yield 2x1 e to the x2, x3. Differentiating with respect to x2 means we have this x1 squared. That's just treated as a constant. And then we need to differentiate this expression here with respect to x2. So that means we get e to the power of x2, x3. And then we have to use the chain rule and we have to differentiate the inner function, this one here, with respect to x2. And that yields a factor of x3. And of course, the same idea works for differentiating with respect to x3. Again, we get this x1 squared, we get this e to the power of x2, x3. Another difference is, of course, if we differentiate this inner function here with respect to x3, we get an x2. So here we get a factor of x2. Okay. To simplify things just a little, there's a common factor of this e term. This is common to all the components here, and x1 is also in all components. So we can factor that out and say, well, that's the same thing as x1 times e to the power of x1 of x2, x3 times 2. We get x1, x3. And here we get x1, x2. Okay, so that's the Jacobian of the function f. Now the function g is conceptually much more simple. Only difference is it has a vector valued output but the computation of the Jacobian should not be that troublesome. This is going to be a 2x3 matrix. We have 2 variables in the input, 3 rows in the output, so 2x3. And we start by differentiating that line here with respect to x1. That's going to yield a factor of 2. And if we differentiate that with respect to x2, we get a factor of 1. So that's the first row. For the second row, differentiating with respect to x1 yields a factor of 1. And if we differentiate with respect to x2, we obtain a factor of -1. So the row corresponding to that second factor here is 1 minus 1. And finally, for the third row, x1, that's a 1 for x1, and the partial derivative with respect to x2 is 0. So that's going to be 1, 0. And as you can see, that Jacobian is actually constant, unlike the one for f, which still contains the variables x1, x2, x3. That's not a constant one. Okay, so these are the the derivatives of f and g. Questions about those?
Yes. So there's one question. Could you explain again under which conditions the differential of a function is equal to its gradient transpose?
So for a differentiable function, we already stated that basically the gradient or the transpose gradient is the only possible differential. You will remember, hopefully, that we defined the total differential basically as an approximation by saying we approximate the function f of x through its function value plus some g transposed x minus x0 plus some remainder. And this g transposed, the vector, so for real valued functions, the vector that yields the linear part of that transformation, of that approximation, that is going to be what we call the differential, right? So we already established that if a function is differentiable, then the only possible candidate for this part here is the gradient. Okay, so the only thing we can do basically is put in the gradient of the function f at x0 here. Of course, a function that has a gradient need not be differentiable, but if it is, then that's the only thing that can happen here. And we did a similar thing with vector valued functions, where you basically changed that just a little by substituting that g transposed by the Jacobian at x0. And again, plus some remainder. So again, we want an approximation, a linear approximation, and we get that by having a function that basically looks like this. We have some constant vector this time, plus matrix times a vector. So that's the linear part of that approximation. And that matrix here that does the job, that's called the Jacobian. And again, we can establish that this can only consist of the partial derivatives if it actually exists. Okay, and now basically the only difference is that here with the gradient, we have a column vector. So if this product here is to be meaningful, then we have to compute transposed column vector times x minus x0. Right? That's a product of basically two column vectors. So the first one has to become a row vector so that this is actually a scalar product. And here we have a matrix vector product. So we don't do the transposition thing here because it's way easier without transposition. So basically the matrix corresponding to this situation here is that G transposed. right? So if we talking in terms of this matrix here, then we need that to have a suitable dimension. And basically for real valued functions, that suitable dimension would mean it needs to be a line because the output needs to be a real number, right? And this x minus x0, that's a column vector. So if we want that to be a scalar product in the real value case, we need to have a row times a column of equal size. So this thing works. And yeah, again, these definitions, those are basically the same. This is a more general version because it works in higher dimensions as well. But of course, it contains this case here as a special case. And in order for that to work, we need to have this row vector here, and that needs to be the gradient transposed. Because again, by convention, the gradient is usually written as a column vector. And that's why we want a row vector here, so we transpose it. I hope that answers the question.
Yes, he already said thank you. So another question as well is, what is the dimension of the Jacobian? Could you repeat it?
So the dimension of the Jacobian, that is simply obtained. Remember, the Jacobian is obtained by taking all these coordinate functions here, and for each of those coordinate functions, we're computing all possible partial derivatives and write those in a row. So that means the number of rows of the Jacobian is determined by the size of the output of the function. So here we have 3 coordinate functions in the output. That means we'll have a Jacobian with 3 rows. And the number of columns is obtained by the number of partial derivatives that we can compute. And that, of course, corresponds to the number of variables in the input. 1 partial derivative for each input variable. So in this case, 2 input variables, that means we get 2 columns, right? So this here, number in the codomain, the dimension of the codomain basically is the number of rows. The dimension of the domain is the number of columns of the Jacobian.
Yes.
Okay.
So meaning here you will have a 3x2 matrix.
Right.
And
here you have a 3x2 matrix, yeah.
I think
and in the case of F, for example, so basically you have a 1-dimensional output, a 3-dimensional input, so you get a 1/3 Jacobian.
Yeah. Good. That was it.
That's it. Good. So let's continue with part B. So in B, we are now considering the function f after g. So that means we first apply g to an input and then f to whatever g made of that. And that's going to give us the output of our global function f after g. And remember g was a function from R2 to R3. So we start with a 2-dimensional input. We produce an intermediate result in R3, then apply f, and we end with a real number as the output. So basically that corresponds to this chain here. So we apply g first, the inner function first, then the outer function to the output, and we end up in R. So this is combined a function that starts in R2 and the output is in R. So R2 is the domain, R is the codomain. Okay, and what we want to do is we want to compute the derivative of that using the chain rule. And of course, you could also do that directly by just substituting g of x1, x2 into f, and then you get an expression for that function f after g, and you could differentiate that. In this case, we'd like to use the chain rule for practice. And the chain rule works almost the same as in 1-dimensional calculus. So the difference is, of course, in this case, the output is different in the dimension. So as we've discussed before, the output here is 1-dimensional, the input is 2-dimensional. So that means the Jacobian derivative of that function here is going to be a matrix that has 1 row and 2 columns. So a 1/2 matrix. And remember how the chain rule works in the one-dimensional case. What you do is you differentiate the outer function first. Outer function is f, the one that's applied last. You compute the derivative of that, apply that to g of x, and then you multiply by the derivative of g. And basically the same thing is happening here. So this Jacobi matrix of f after g of x1, x2, that can be obtained by computing the Jacobi matrix of f at the point g of x1, x2, and then multiplying by jg of x1, x2. And contrary to one-dimensional analysis, of course, this here is a product of two matrices. So the order is now essential. You cannot change the order without changing the result. Usually the result will not even be defined if you do that. So you have to stick to that given order in the multidimensional case. Otherwise, the rule is basically the same as in one-dimensional calculus. Okay, so that's what we're going to do. We already know JF, we already know JG. So basically what we need to do is we need to compute JF at the point G of x1, x2. Now G, again, is simply given by 2x1 plus x2, x1 minus x2, and x1. And you remember that JG is simply a matrix. I'll write it down in the next step. So let's first take care of this JF here. We computed JF up here. Now this here was the expression for JF. Let me just copy that. Okay, so remember JF of x1, x2, x3 was this expression here. And now we want JF evaluated at these coordinates. So instead of x1 in this expression here, we use this term, 2x1 plus x2. Instead of x2, we use this term, x1 minus x2. And instead of x3, we use this term, x1. Right? So this is not j at x1, x2, x3, but jf at this vector here. Okay, so what do we get if we do that? Well, so that starts by x1. x1 is 2x1 plus x2 here. So we have 2x1 plus x2 times e to the power of x2 times x3. So that's this times this. So x1 minus x2 times x1 times, now we get that matrix here, it's 1 by 3 matrix. 2 is, of course, a constant again. Then we have x1, x3, so that means this multiplied by this. So we get 2x1 plus x2 multiplied by x1 and x1, x2. So that means this multiplied by this. So that's 2x1 plus x2 times x1 minus x2. And that's this first matrix, JF at G. And we need to multiply that by JG, the Jacobian of G, which we computed as well. That was simply this constant matrix here. That's much easier. That means we want to multiply that by the matrix 2, 1, 1, minus 1, 1, 0. And you can see here we have a matrix that is 1 by 3. Here we have a matrix that is 3 by 2. So the middle dimensions agree, 3 and 3. That means we can actually compute that matrix-matrix product. And the result will be a 1 by 2 matrix. And remember, that is exactly what we expected it to be, 1 by 2 matrix. Okay, so the result will be in 1 by 2. And now all we have to do is make the necessary computations. And what we get is, well, this factor here right in front, we can just leave that as it is. 2x1 plus x2 e to the power of x1 minus x2 times x1. And then we get this 1 by 2 matrix here. To make things a little nicer, I write this as a 2 by 1 matrix and then transpose that, so that I can fit it all in one line. So the result of this is going to be, now here we get first column first. So we have 2, 1, 1. 2 times 2 is 4. 1 times this factor here. So that's plus 1 times 2x1 plus x2 times x1 plus, and then 1 times this factor here. So that's 1, sorry, I wrote that 1 already. 1 times 2x1 plus x2. Oops. Yeah, should be here. Times x1 minus x2. Maybe I can write that in a readable way. That should do it. So that's the first column of the actual matrix. Remember, I transposed that. And for the second one, that's a little easier. I need to multiply this column here with this row. So I get 1 times 2. That's simply a 2. Then I have minus 1 times this expression here. So I get minus 1 times 2x1 plus x2 times x1. And finally, I get 0 times this expression. So I just write plus 0 to clarify where this comes from. So this is the expression that we get for the Jacobian of f after g. And that completes part B of that question. Any questions about that?
No, not really.
No questions. Okay, wonderful. Well, that's not the case. Then let's discuss polar coordinates quickly. We'll be done early today. 5.3. Polar coordinates. You remember polar coordinates is a way of describing points in the plane. So we first discussed planar polar coordinates. Not in the usual way as Cartesian coordinates, but instead by giving a radius and an angle for every point. So if we have a look at the usual Cartesian coordinate system, this one here, x1, x2, and if we consider a point like this one here, for example, so that's our point, let's call it A, then it can either be described as x1, x2 by these Cartesian coordinates, or in the case of the polar coordinate system, what we do is we instead describe this point through the length of that line here, that is called the radius, and the angle above the x1 axis, and that is called the angle or the argument of that point. So that is what we call polar coordinates in the plane. And of course, if we have this radius here, and the angle, then we can describe each point in the plane, basically. Often the radius will be restricted to, well, the radius will be restricted to numbers that are either 0 or positive, so non-negative numbers. Negative radii don't usually make sense. And the angles will usually be restricted to values between 0 and 2 pi. So an angle here on that circle here is valid. You don't have to do that, of course. You could also allow for negative angles, or you could allow for more than one rotation. It would also be fine. It just makes the description less ambiguous if you do that restriction, but that's not strictly necessary. And sometimes it will be a valid choice and easier if you use negative values for the angle, for example. That's pretty common, actually. So we define these coordinates basically by a transformation that, given radius and angle, yields the corresponding Cartesian coordinates. And that works, we'll call that T. That transformation works by assigning to a radius and an angle phi the corresponding Cartesian coordinates, and those are simply given as r times cosine of phi and r times sine of phi. Right, so this is the transformation that maps Cartesian coordinates into polar coordinates into Cartesian coordinates. And of course, with suitable restrictions on radius and angle, you can invert that function to get from Cartesian to polar coordinates if you want to. Why this is actually useful will hopefully become clearer at a later stage during this lecture, specifically when we talk about integration over certain bodies. And sometimes it's easier to describe these bodies or fields by means of polar coordinates. Or in 3D space, the analoga would be cylindrical coordinates or spherical coordinates. Now, in C53, what we have to do is we simply have to devise a description of a certain set in polar coordinates. That set here, let me show you that. Looks like this. So that blue set is the one that we want. You can see if we had to write this in terms of Cartesian coordinates, x1, x2, and then give restrictions to those, that might not be very convenient because we have this circle, it's part of a circle here. So basically this thing is the segment of a circle, a two-dimensional piece of cake. In polar coordinates, it's not hard to describe that actually, because what you can see is this here, the radius, the distance of those points here from the origin, it's always the same. Right? So we actually have a circle. So the radius is simply between this upper bound, and as you can see, any point below that line is also included in the set D up to this origin here. So any radius below that bound will also do. And the same is true for the angle. Every point above this angle here is included in D up to, now this here is the upper bound, up to this angle. So basically radius is bounded below and above, and the angle is bounded below and above. We just have to define those bounds, and then we're good. And if you look at that set, it's easy to see the bounds, hopefully. Let me just give a quick sketch here so we have that in the notes as well. So basically, set looks somewhat like this here. So that's our set D. The radius here, as clearly indicated here in the sketch, there's a 2 here, so the radius is obviously 2. Radius is 2. The upper bound is 2. The lower bound, of course, is 0. And for the angles, well, this here is the starting angle. And this here is the upper bound for the angle. The starting angle, you can probably guess what that is, or you can see as the line passes through these 2 points here. So that's supposed to be an angle of pi over 4. And same thing here, line passes through these 2 points. So that's an angle of 3 pi over 4. Okay, so that here is, oops, sorry, wrong color on the screen. So, well, this is pi over 4. And this blue one, that is 3 pi over 4. So we can describe this set D right away. So D is the set of all x1, x2, all Cartesian coordinates obtained as a transformation from the following polar coordinates. So T of R and phi of, well, we said the radius is going to be between 0 and 2. And the angle is going to be between pi over 4 and 3 pi over 4. And that's the description of that set in polar coordinates. Basically, that's all I wanted you to do here. Questions about that one?
So far I only have someone typing, so maybe you could answer the one about holiday next week while we wait.
Yeah, not a lot to answer about that. So there obviously there is a holiday next Monday, Monday after Whit Sunday. So you all have a day off. And that also means there's not going to be a central exercise session. So the following sheet will not contain any C problems. I do hope that will not be too troublesome. I'll save some time for the questions on that sheet on these topics for the coming week. So sheet number 6 will only have homework problems. And of course, you're welcome to ask about those in the tutorials on Thursday, which will take place. And sheet number 7 will then again contain central exercise problems, and we'll discuss problems on the following week's topics as well.
And will you release equally many videos as you normally do?
I try to reduce the number of videos just a little so that you have, I really can enjoy your day off.
Okay.
Or take some time to recap what you may have missed so far.
Even better. So now I have a question about this exercise. How would you proceed if the angle and the radius is not so easy to see?
Well, basically, this all depends on you being able to somehow devise the angle and the radius. So the question here is, what do you mean by not so easy to see? Probably what I would do is spend more time on that and try to figure out what the angle and the radius does. And we'll do some more of these problems in the future. So you'll have some opportunities to practice that.
Okay, another question. So just by stating polar coordinates, we already know that we are restricted to some circle.
We're not restricted to a circle, but basically everything that looks like a circle is easy to describe in polar coordinates. And that's why we do that, right? If we had a square, polar coordinates would obviously not be a good choice. We'd better stick with Cartesian coordinates. So the point here is we have a couple of different coordinate systems that are useful in different situations. And basically your task is going to be to find out which coordinate system is the best for the task at hand. And usually if there is some circular looking part, then you should try polar coordinates. Yeah, and of course that does not mean that the radius cannot change. Maybe it does change. So maybe instead of a thing that looks like this, for example, you could also have something that looks like this, right? So a spiral where the radius does change with the angle. The important point is that there is a functional connection between radius and angle that you can describe in a meaningful way. And then polar coordinates might be a good choice.
Yes, another question as well. So they're wondering how well they're doing in terms of the quizzes.
I haven't actually looked that up. I should, yeah. I'm going to talk to my quiz master and see how well you're doing.
Okay. Will you maybe post on Moodle?
I'll post that to Moodle, yes.
Okay, good. And then there's another, oh, now they're starting about the exam. Do you already have information? Because
unfortunately, no, I'm still waiting for feedback from your department. So that is not my fault. I'll send them a reminder today.
Yeah, they So someone said it looks like it's going to be online from tomorrow, but that's not decided, right? That's what you're saying.
It's not, it hasn't been a final decision. So I'm leaning towards an online exam. Basically, so that we all can make plans that will not fail 2 weeks before the exam then. And also to give everyone who's currently abroad and might not be able to come to Germany in time with all the quarantine rules that might be in place or might not be in place at that point. We just don't know. To give everybody a chance to actually do the exam. I'm leaning towards online, but I'm still waiting for official confirmation here. I'll let you know as soon as I have word from your department.
And then there's someone that wants to ask questions about the sheet, so the homework problems, but that probably does not make sense here, right?
Yeah, so for the homework problems, it's probably better to ask in the tutorial sessions so that we can discuss all your problems on the homeworks on a very individual basis. So you're welcome to join us on Thursday in the tutorials. We meet at 2 and the tutorials last up to 5 o'clock. So 2 o'clock to 5 o'clock every Thursday, unless there's a public holiday. Just join the Zoom call. The link is on the Moodle page, and you're welcome to ask any questions about the homework or the central exercise sessions or anything else in the tutorials, and we'll be happy to answer.
Yeah, but it's a bit of a shame to give away an exercise here before people even.
Yes, probably, yes, yeah.
Okay, but what about the exam date that was published?
The exam date that was published, that should be I don't really know what the date was, but
it says,
that should be fixed.
So it says 2nd of August from 8 to 9:30.
That seems like a very bad time, but yeah, I don't have any influence on that. So yeah, that's fixed.
Okay. And then I don't see any more questions.
Okay, great. Then we're done a few minutes ahead of time today, which is nice.
We're making up for
yeah, making up for all the times that I haven't been on time. So I'll see you, hopefully I'll see you on Thursday in the tutorials, or otherwise remember no central exercises next Monday. So I'll see you in 2 weeks time in the central exercise class once again. Thanks a lot to Eileen for moderating the chat and answering all of your questions that I haven't been able to answer. So, goodbye.